In mathematics, epsilon is a number such that when you square it, the resulting value is 0. Despite this, epsilon itself is not equal to 0. Values that are composed of a real part and epsilon part are known as dual numbers and are often represented in a two-dimensional plane, similar to complex numbers. Dual numbers are usually of the form a plus b epsilon, similar to how complex ones are generally of form a plus bi, where I squared is -1. You can do many types of operations with dual numbers: addition, involving adding the real parts and adding the epsilon parts, and similarly for subtraction. For multiplication, you can use the distributive property, with the last element canceling out due to the epsilon squared equating to 0. You can also perform division with dual numbers, however it is slightly more messy. The property of epsilon that we will be taking note of is that plugging x plus epsilon into a function gives the sum of the output of the function itself and the derivative of the function at x multiplied by epsilon. This property can be seen through representing functions as a Taylor series. A Taylor series is an infinite polynomial that models functions using higher and higher order derivatives. Some common examples are e to the x, which uses the Taylor series 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on, as well as sine of x given by x minus x cubed over 3 factorial plus x cubed over 5 factorial minus x to the 7 over 7 factorial, and so on. If you want to learn more about it, I'll leave a helpful video by 3blue1brown in the description. Now, to plug in our x plus epsilon to one of these Taylor series, it is apparent that we need to have some way to find x plus epsilon to any value n. Fortunately, we can do this using the binomial theorem. This theorem states that for any 1 plus x to the n, it will be equal to 1 plus nx plus n times n minus 1 over 2 factorial times x squared plus n times n minus 1 times n minus 2 over 3 factorial times x cubed, and so on. We can utilize this by factoring out x to the n from our x plus epsilon to the n to get x to the n times 1 plus epsilon over x to the n. Then, using the binomial theorem, we can say that this will be equal to x to the n times 1 plus n times epsilon over x plus n times n minus 1 over 2 factorial times epsilon squared over x squared plus n times n minus 1 times n minus 2 over 3 factorial times epsilon cubed over x cubed, and so on. However, through the fact that epsilon squared is equal to 0, we know that for any n larger or equal to 2, epsilon to the n can be represented as epsilon squared times epsilon to the n minus 2, with the epsilon squared dissolving to 0 and nullifying the rest of the expression. From this, we can cancel out all parts of our prior expression that are a factor of epsilon to any n power above or equal to 2. This yields x to the n times 1 plus n times epsilon over x. If we use the distributive property here, we can find that x plus epsilon to the n is equal to x to the n plus n times x to the n minus 1 times epsilon. Interestingly, the epsilon part of this expression, n times x to the n minus 1, is actually the derivative of x to the n via the power rule. So, we can say that if f of x is equal to x to the n, then f of x plus epsilon will be equal to f of x plus f prime times x times epsilon. Now that we have a simpler version of the problem, we can return to our Taylor series. Importantly, due to the linearity of derivatives, the sum of two derivatives is always equal to the derivative of the sum of the original functions. Applying this to our Taylor series, we can see that plugging in x plus epsilon will yield the original power, as well as its derivative times epsilon. Then, because of linearity, we know that the derivatives and original functions will group up together, giving us that f of x plus epsilon is equal to f of x plus epsilon times f prime of x.